Okay, so mostly I'm going to be talking about work that was done by Lenoy Meshulam, who finished her PhD last fall and is now a postdoctoral fellow at MIT. We had the good fortune to collaborate with extraordinary experimentalists who are in the middle of the author list here. And I'll tell you more about the data that, the setup of the experiments that we're analyzing once I give you the theoretical background. The ideas that I'm talking about are contained in two preprints that are on the archive, one short and one long. The short one may not contain much more than what I managed to say in an hour and a half, but the long one I hope does. And there's also some background in a theoretical paper that Serena Brade and I wrote now a couple of years ago. So I'm going to be talking about networks of real neurons, but really the question that's driving us here is, why is it that we think we should be allowed to write down simple models for something as complex as a network of neurons in the brain? You all know that if you try to write down a moderately realistic model of a biological system, starting at some microscopic or even mesoscopic level, it's enormously complicated. There are lots of parameters, there are lots of variables. If you take seriously every little thing that has been noticed, then it's impossible, right? It's unbelievably complicated. Physicists, of course, we are greatly enamored of simple models, and to the point where there are even jokes about it. I understand everything's recorded, so this is actually not a particularly dirty joke, but I'll skip it anyway. But the clash between the physicists' search for simple models and the biologists taking seriously all of the microscopic details is the source of a lot of challenges in our community. And I think sometimes we talk past each other. In particular, I think that when confronted with the question of why are you writing down simple models, as physicists we often don't give as thoughtful an answer as we should, or as deep an answer as is possible given what we have learned. So there are two very different reasons why it's possible for us to write down simple models to describe the world. One is that the world really is simpler than it might have been at the microscopic level, right? So there are fundamental building blocks. The rules for how they interact with each other are not arbitrarily complicated. They're strongly constrained by symmetries and all that. And out of the interactions of those elements, you can build up enormous complexity, despite the fact that what you're starting with are relatively simple models. Okay? That, I don't think, is the argument for why simple models would work in a biological context. Because although it's true that at the level of atoms and below, there are a small number of components, there are a small number of fundamental constituents, and the rules for their interaction are relatively simple, that's not the level at which you would start in a biological context. You start by talking about molecules, and the molecules already themselves are very complicated, and there are thousands of different kinds of them. And so, in fact, at that semi-microscopic level, it's not true that biology is that simple. It's maybe simpler than sometimes made out to be, but it's not that simple. So, to put it, so there's another way in which simple models work in the physics problems that we understand, and that is that the simplicity emerges when we pass from the microscopic description to the macroscopic description. And so the example that probably will resonate with most of you is you all know about the Ising model, and I hope you all also know that there is no real ferromagnet whose microscopic description is exactly a collection of Ising spins interacting with their nearest neighbors. Okay? So an important answer to the biologist who asks, why are physicists constantly oversimplifying the biological reality is, possible answer is, don't feel special, we also oversimplify non-biological systems. But you also know that it works, right? It works qualitatively in that you get out a phase diagram, which is the phase diagram of real magnets. And it works quantitatively in that since you've written down a model which is devoid of microscopic detail, you're necessarily predicting that many features of different magnetic materials must be the same if measured in the right units, quantitatively, because there's no place in the model for you to tell what the magnet is made out of. And of course, this is the idea of universality. And at near a critical point, that universality is quantitative. And the models that we write down allow us to predict the behaviors near a critical point with, well, I think the limit on measuring critical exponents in magnetic materials is something like 3 decimal places, and they agree with experiment, right? And the theory and experiment agree, and again, those theories make no reference to the microscopic details of what the material is made out, what the magnetic material is made out of, which is telling you that somehow in going from trying to describe the microscopic physics to describing the behavior on macroscopic scales, something simplifies. So, roughly speaking, this is the simplicity which is the business of our particle physicist friends. This is the simplicity which is the business of our condensed matter physics friends. And if I had to bet, I would say that it's this kind which is more likely to be a guide in the biological setting. But that shouldn't prevent somebody from trying the other one, right? So that's what we're going to talk about today. And we're going to take this very seriously. We're going to ask, okay, let's go back and think about how that simplicity emerges, and then ask whether we can follow the same path in looking at a real network of neurons and look at the actual data and see if that guides us to similarly simple emergent behaviors. And let me emphasize that when we actually get back to talking about real neurons, it's going to be entirely phenomenological. Okay? And I think the phenomenology is really interesting and points toward what a theory might look like and what the challenges are, but we don't have that theory. So, okay, just so that you know what's coming.
Sorry,
yeah.
I've been nitpicking a bit, but about point 1.
Yeah.
If you look at the entire expression for the Hamiltonian of the standard model, it doesn't look particularly simple to me.
Yeah. So.
And I think that's a debate that also agitates the particle physics.
Absolutely. So I think.
Considering what it describes.
Okay, let me put it this way. Maybe instead of why do, we could say why could. So what's the ideology behind the search for simple models? So one ideology is all the complexity that you see is a distraction, and if you just get down to what's fundamental, you'll see that it's much simpler. So that's the particle physicist view. And you know, it's a matter of analyzing the history of physics to ask how successful has that been, where does it find its limits, and so on. I mean, right, the discovery of the muon was already greeted with the worry that things were getting too complicated, right?
Discuss is the word you look.
Yes, that's right. So, you know, it obviously, whether the community thinks they're succeeding in this enterprise kind of oscillates with time, but it's also true that there's the standards are changing, right? So let me give you a better example. Roughly speaking, I can derive the entire periodic table by knowing one parameter, which is the fine structure constant. And that gives me all the rules of chemistry. Okay, that's pretty good, right? It's not quite right if you're in the region, if you're in the, you know, the transition metals, right? Because then the relativistic behavior of the electrons matter. So it's not quite right. So, so if you give me the periodic table up to some point, right? Right, that's right. Yeah, just a small problem. So, right. So I think both of these are both ideological approaches, right? And they have concrete results behind them. And then you can, you know, it is never the case. What is the saying when you Want to go invest money? Past performance is not a guarantee of future gains, right? Something like that. So, just because things worked in the past doesn't mean they'll keep working. But I think you all know that this path has been enormously productive. We've learned a lot by trying to do this, even if at some moment you feel the rough edges. And this really, of course, was one of the great discoveries of the second half of the 20th century, right? Leo.
I mean, it may be that's my view, that 1 and 2 actually just distinguish by ideology, but not actual content, because what you call microscopic is maybe something like
Yes.
pretense of high energy physics, meaning that they have the fundamentals. I mean,
Right.
They have many decades of scales that maybe nothing is happening, maybe.
Yes.
And as a result of that, what they would call microscopic and simplicity is maybe a consequence of 2.
Yes, exactly. So
It's not maybe ideal.
let me put it this way. If you're trying to explain to somebody, so let me zoom out, right? And then I actually want to dig in because time marches on. These semi-philosophical introductions are very dangerous. If you want to explain to somebody why is it that you're even going to try using a simple model in a complicated setting, I would say that these are two very different kinds of arguments you might make. And they will be backed up by different examples. Whether in the end they're really different or, where we're going to end up along either of these paths, that's more complicated, right? Okay, is everybody with me? So, again, let me just say it once more, right? The Ising model doesn't describe the microscopic physics of any real magnet. And as you all know, if you were for some reason confused and thought that it described a real magnet, then you could say, well, maybe I should think about the Ising model as a lattice gas, right? Spin up is there's a molecule in this little box. Spin down is there's no molecule in the little box. And then you have a theory not of the ferromagnet-paramagnet transition, but of the liquid-gas transition. And if you can look at the Ising model and think that that's a microscopic description of molecules interacting with each other in a gas, good for you, but I'm pretty sure it's not, okay? So the reason that you get things right is not because you get the microscopic physics right. Okay. So let's see. Let's do some work. I can do that over here too, right?
Just remember that the board doesn't move.
Yeah. So what is the idea? So actually, you will not be held accountable for this, but how many of you have had a course where there was a reasonably thorough discussion of the normalization group? Fantastic. Okay. So
Leo?
maybe you taught one. So I'm going to assume that so there's no way that if you know nothing about the normalization group, I can tell you enough in the next 15 or 20 minutes. I'm hoping that most of you have heard, apparently a lot of you have had a real course. I'm hoping the rest of you have at least heard some of these ideas. And if there's really something that's confusing, you should stop me. I'm hoping that even for those of you who know this material, the emphasis might be a little different than what you usually get. So there's something for everybody. So what's the idea? Let's think about what it means to describe a system. Let me, for the sake of simplicity, think about systems that are in thermal equilibrium. Obviously, if we're going to talk about networks of neurons, we'll have to get away from that. But in particular, let me think about systems that are in thermal equilibrium, and let me think about describing the distribution over states. So you all know, so if I have local variables, sigma I, then what I want to describe is the probability that you will find these local variables all of the local variables. Remember, there's a large number of degrees of freedom, right? I want to describe the joint probability that these will all be found in some particular state. And you know that if the system's really in thermal equilibrium, then this is the Boltzmann distribution. And what does it mean to say that that I'm looking for simplicity to emerge as I try to describe macroscopic phenomena? What I mean is that somehow the original variables are defined on some microscopic scale A. So for instance, if you're thinking about the Ising model, the sigmas are actually the spins. They live on a lattice. The lattice spacing is A. Okay? So it's the scale of atoms in the system. So now let me imagine defining some coarse-grained variables on scale L. So how am I going to do this? I'm going to be specific in just a moment, but conceptually, imagine that you're looking at the system under a microscope and you just defocus the microscope. Okay, so you used to be able to see every single spin. Now all you see is some blurry thing that tells you that in this neighborhood, most of the spins are up. In this neighborhood, most of the spins are down. And the size of your neighborhood is L. Okay? So now you can ask, what is the probability distribution on scale L okay? So I don't want to know every microscopic detail on length scale A. I only want to describe the variables on length scale L. Well, I started with the Boltzmann distribution, and I can write the energy as a sum of terms, which for reasons that have to do with the connection back to particle physics, to quantum mechanics problems are referred to as operators. Right? So I can take the energy and I can do something and I can expand it in some way. So my variables can interact with themselves, they can interact with their nearest neighbors, they can interact with their next nearest neighbors, they could interact in groups of 3 or 4 instead of just in pairs, whatever you want. Okay? I can think of the probability distribution that I end up with over here as being also a Boltzmann distribution. And I can use the same basis that I used for expanding the energy, again, with the new variables. Now, strictly speaking, you should worry, right? If you blur things, you don't actually have the same number of variables anymore. So if you really want to be precise about this, you should also zoom out and imagine that you can see a larger system so that the total number of degrees of freedom stays the same, which is clearly a theorist's idealization, and we're going to have to lose this when it comes to real data. But just to be precise, right? So I started with n variables on a scale A. I blur to scale L, and I zoom out so that I again have n variables, but it's on scale L. And then I look at what happens in the transformation from G1 which is on scale A, to let me do it this way, on scale L. Right? So what does it mean to say that my model got simpler? What it means is that if at this level I needed lots and lots of coefficients in order to explain what was going on, spins interact in groups of 4 in little plaquettes, they interact with their third nearest neighbor, all sorts of other things. As I allow my coarse graining scale to get larger, most of these coefficients go to 0. Okay. So 2 things can happen. One is that either, if you imagine doing this smoothing out continuously so that you can change L gradually, then you can think about what's the derivative of these coefficients. So it could be that it's larger than 0. Well, then in that case, that term in the energy is becoming more and more important as you go to longer and longer length scales. And these are called relevant. But if it's less than 0, then what that means is that that term is becoming less and less important. And in fact, in some sense, you didn't need it in the first place. Because by the time you get out to describing things on a long length scale, that term will have gone away from your description. So these are called irrelevant. So there's a quote.
Sorry,
Yes?
so doesn't that depend on the base in which you decompose your operator?
The way I've said it, yes.
What's a comment?
So the way I've set this up, it matters what coefficient, it matters how you did this expansion. But of course, I can always rearrange the expansion. So first of all, in many cases, there's a natural, so this brings up several points, okay? Let me get back to this in just a second before there's a related question. Yes, oh, yes. Let me, you know that I don't want to, anyhow. Right, so the set of people who raised their hands near the beginning know what I'm fumbling about. Yeah, that's right. So you should be a little bit more, yeah, this is a transformation. You should think about doing this in the limit as L becomes large. As L becomes large, the transformation approaches some fixed point, and you ask about the eigenvalues in the neighborhood of the fixed point. That's the correct way to do it, but I was trying to do this in a way which was still friendly for the people who didn't raise their hand in response to my question. And I may now have failed, right, in the search for honesty. So, right. Is there a trade-off between honesty and comprehensibility? That's an interesting. Part of education is to lie just a little bit, right? So the way I would summarize this is that it is remarkable that we have a field of science in which irrelevant has become a technical term, right? It has a precise mathematical meaning. It means that if you put that term into the microscopic physics, by the time you try to describe physics on a macroscopic scale, it will have gone away. So it embodies mathematically your intuition about what irrelevant means. So as you all know, right, this setup is called the renormalization group. It was finally brought to its modern formulation by Wilson in 1971 after many ingredients before that. And I have heard it said, but not for attribution, because I heard it attributed to someone who has since denied saying it, that irrelevant operators were Wilson's greatest discovery. That is to say, the discovery is not, well, there's of course the whole structure, but the fact that in this structure, most of the terms that you would write down at the microscopic scale go away when you go to the macroscopic scale. That's the profound realization. That's what makes universality possible. That's what makes it possible to write down a simple model and get the macroscopic physics right. So if there were a few irrelevant terms and lots of relevant terms, then you'd have to get all the relevant terms right if you wanted to describe the physics on macroscopic scales. But in fact, it's the other way. Most of the terms you write down are irrelevant. So there's a very simple calculation, which you should all do in detail if you've never done it before, which illustrates this. And this is to do the one-dimensional Ising model, which, by the way, doesn't do anything interesting. Okay? But it has a very important feature, which is you can do all this exactly. So in the one-dimensional Ising model, the energy is just this. And so how do I do my coarse graining? Well, the simplest way of doing the coarse graining, actually, is just to average over every other spin. So instead of writing down, so if you think about now, let's say what's happening here, I have in the energy for this, so this is n plus 1, and n plus 2. So the energy looks like minus j. I'm gonna integrate over this spin, right? So the only thing I care about are the terms in the energy that depend on this spin. And that's sigma n plus 1, and sigma n plus 1, sigma n plus 2. And so you take the probability distribution, e to the minus beta e, which depends on all the spins, and you sum over all of the odd spins, right? Let's say all of the spins whose index is odd. So let's do it 2n plus 1, 2n plus 2. Okay. So if you work through the algebra, and actually maybe you don't want to do the algebra, you just want to look at the problem, right? If I take this spin out, then these two spins look like they're interacting with each other, right? Because they're each interacting with this one, but you don't see it. But importantly, this spin does not suddenly start interacting with this spin. By removing the spin in the middle, because things are only coupled to nearest neighbors and because you're in one dimension, you end up with a model in which the spins that are left still interact with each other only with nearest neighbors. So that means that this becomes another Boltzmann distribution. And in this new Boltzmann distribution, I have another coupling constant that connects sigma 2n and sigma 2n plus 2 summed on n. So in this particular problem, what you find is that you can blur out your description and you get back exactly the same model you had before, just with a different value of the parameter. Okay, that's why you want to go through the algebra and see exactly how it works. It's very simple. And if you want to, you can add a magnetic field. That still works. If you really want to, you can do the one with second nearest neighbors. It's a little more complicated. Okay. The important thing in this problem is that if you work it out, the absolute value of j prime is always smaller than the absolute value of j. And what that means is, as you zoom out and coarse grain your description, the spins become less and less strongly interacting until eventually they're not interacting at all, and that means that there is the system never orders. Right? So actually, it's kind of a trivial model. The only reason you do it is because you can work out all the details. As you may know, this was Mr. Ising's PhD thesis, and he figured out that he could solve the problem in one dimension, except nothing interesting happens in one dimension. I think that was it for him, right? We don't hear from him again. So it's kind of a sad story.
I was told that he thought that this would extend to any dimension, so the model was not
Yes. So,
studying at all.
yeah. So when your thesis advisor gives you a problem and it turns out the first version of the problem doesn't work, you probably should not conclude that it doesn't work at all. But on the other hand, it was difficult to make progress at the time. Okay, so this is a problem in which you can do everything exactly. If you imagine trying to do this in 2 dimensions, now you see that things get complicated, because even if things only interact with their nearest neighbors along the horizontal and vertical, as a result of these things, you now have interactions on the diagonal. And in fact, it's worse than that. You start to have interactions among 4 spins together. All hell breaks loose. So famously in 1975, Wilson did this calculation for the 2-dimensional Ising model, which of course can be solved exactly, so you don't need to do this, but to illustrate the ideas. And he followed, so in the 2-dimensional case, you get more terms than you start with a model that only has 1 term in it, then you get a whole bunch of extra terms, and then you get more terms if you do it again, and then gradually all of those terms start to go away. And so what Wilson did was he followed, I tried to look up the number before lecture, it's 217 terms in the Hamiltonian, all these different combinations, right? And indeed, only a small number of them survive, right? 2, actually, to be precise. So we know concretely that, so you just take a model, complicate the model, and you see those things go away as you coarse grain. Yes? I was trying to work my way through the description of this morning just to be sure I remembered, and he did a lot. It's, I mean, this was 1975. It was harder. You could do it. I mean, now it would be an exercise, right? So right. I'm trying to resist doing too much of this. So this is the 1975 paper in Reviews of Modern Physics by Wilson. Yeah. Okay. So so if you want the 2D case. And it's a chapter in the middle of a very long article. Good. Okay, so you get the idea. So now the question is, let me make one other observation here, which is that when I say that you want to zoom out, that you want to coarse grain, there's several ways of doing it. So if I want to do coarse graining, one thing I can do is what's usually called decimation, which is what we're doing here. So this is the trick of averaging over every other spin. Another idea are block spins, and this was actually one of the original versions of the idea before it was completely well developed. So for example, here I have a block 3 by 3, and I notice that 1, 2, 3, 4, 5, 6 of the spins are up. So what I'm going to do is to replace all of these by one big upspin by majority rule. Okay? You could also think about replacing all the spins in this block by a number which measures the fraction of them which are up. And then as you increase the scale in which you're doing that, that will gradually become an estimate of the local magnetization and will become smooth. Okay? The other way to do it is to Fourier transform. So I'm going to take my variables that live at some, I'm going to emphasize now that the variables sigma I actually live at positions xi. I'm going to write those as being a sum over wave vectors k e to the I kxi sigma k. And then I'm going to produce coarse grained variables by saying that the way I have coarse grained variables at scale L is to restrict my sum over wave vectors to be less than 1 over the length scale L. Okay. And you might want to worry about how you normalize these variables. So you should put a factor out in front. Okay? So these techniques are called real space methods. And these techniques are usually called momentum shell methods. And the reason it's shell is that if you change L by a little bit, then what you've done in trying to construct, in trying to figure out what happened to the energy function, you're averaging over, sorry, let me say this more clearly. What you're doing when you make this replacement, right, is you're excluding from consideration all of the sigma tilde of k that have k larger than your cutoff 1 over L. So those are all the short distance, short wavelength variations, right? And if you think about trying to compute the probability distribution, what you're doing is averaging over all those short wavelength fluctuations. If you now move your cutoff, you have to average over another thin shell of wave vectors. So that's where the name momentum shell comes from. Okay? Good. If you're calculating with pen and paper, you would probably do this. And if you were calculating via numerical simulation, you would probably do this. And that's important, right? Because we're going to do something with real data, so you have to think a little bit about what you want to do. Okay, let me stop for a couple minutes and see how we're doing. Do people understand what's going on? Again, many of you have spent a semester on these topics or more. Okay, remember the goal is not to make these constructions, but to try and follow the probability distribution of the variables that are left. Right? That's the thing that we're interested in. So, you could say, all right, armed with all these techniques, go to work on the biological system that you care about the most. So what's the problem? You'll notice that with real space methods, you need a notion of neighborhood. in fact, I talked about this whole idea as changing the length scale on which you're looking. So you have a notion from the very beginning that things are interacting somehow with their near neighbors, and that the details that you want to average over are the details on short distances. So if I have a network of neurons, what am I going to use as a notion of neighborhood or distance? Well, you could say neurons are laid out in space, so why don't you use actual distance? Well, the problem, of course, is that neurons, each individual neuron deep in your brain is connected to thousands of other neurons. The physical range of those connections is vastly larger than the spacing between the neurons. And so, yes, on some very large scale, it's probably true that local neighborhood means something, right? So if you're studying functional magnetic resonance images of the human brain, then your spatial resolution is of order a millimeter, and it's probably true that locality is a good guide to interactions on the scale of a millimeter, although even that's not quite true because there are long axons that reach all the way across your brain, right? But still, maybe on the scale of millimeters, if you went from 1 millimeter to 2 millimeters, maybe that kind of makes sense. But on the scale of individual neurons, if you're going to coarse grain, just averaging what neurons are doing with their physical neighbors probably doesn't mean anything.
So Eleni told us today how to define distance based on time, effective time. How to go from one place to another. How long does it take?
Yes. Hold the thought. So people have tried, in the context of models, people have tried to say, well, suppose that the variables that you have live on some arbitrary graph. Then maybe I have notions of neighborhood on the graph that are not the simple, they're notions, they might be notions that are somehow derived from the adjacency matrix, right? Again, in the case of neurons, this might not get us very far because neurons in that sense have 1,000 neighbors. And so maybe I should just go all the way to the mean field limit to start with, but that's probably also not right. Okay. A corollary of the fact that I don't know what I mean by neighborhood is if I wanted to do momentum shell, well, what are the momenta? Right? This is something that makes sense in a system that's translation invariant, right? So the reason you go to Fourier space is because things become diagonal in Fourier space, right? And if things aren't translation invariant, then that's not true. So if we're going to implement these ideas in the context of a network of neurons, we need to have candidates for what neighborhood and momentum mean in the context of a complicated network. Okay? And let me emphasize that what I'm going to tell you about, I think of as being candidates in the sense that there might be other choices that make sense and might even be better. But this is what we've tried, and I'll tell you what happens. Okay? I'm not going to claim that we know for sure that this is the right way to do it. And you could argue that a priori, you have no reason to believe this is going to work, right? Because basically I've stripped away the things that are foundational in the development of the theory, so why should things work? And obviously, there are versions of these problems that arise in other contexts, for example, already in disordered systems, but the problems here are particularly severe, okay? So let me give you some candidates for what neighborhood and momentum might mean. So there is something I know how to compute, and that's a correlation function, right? So if I have variables sigma I, a fundamental object is their covariance matrix. So if you think about problems if you think about systems where the variables live on a lattice and the interactions are generally sort of positive, right? then your nearest neighbor of I is the argmax with respect to j of Cij. Right? Not counting. Right. Not counting your correlation with yourself, of course. Okay? So how do I find my neighbor? I look for the guy that I'm most correlated with. So the proposal, which again may not be right, is to take that seriously and say that what I mean by my nearest neighbor is always the one that I'm most strongly correlated with. So how would I change my length scale of averaging by a factor of 2? What I would do is I would find the maximum of Cij again for I not equal to j. So that will be some I and some j star of I. And then let's take sigma I and sigma j star of I and add them together, and that produces my coarse-grained variable sigma I. And then I repeat. And at the end of doing that, I've taken my original variable sigma I, where I runs from 1 to n, and I've mapped them into a set of coarse-grained variables, sigma I, and I'll put a little 2 there just to be a reminder, and that runs from I equals 1 up to n over 2. Yes?
So this is not reciprocal, right? Like I can be J's nearest neighbor, but then not the other way around.
So the way we're doing this here, so even if I tell you that the intuition is that your most correlated partner is your neighbor, I'm still not done. I have to tell you how you're going to find those. And what I'm proposing here, right, because that's a statement about one, I mean, maybe the stronger way of saying it is, this statement makes sense for one spin, finding its neighbor. But what you really need to do is pair them all up. So how are you planning on doing that? And what I proposed here is a greedy strategy. Right? You find the most correlated pair, you put those together. You find the next most correlated pair, you put those together, and so on. You could think about trying to do this in some self-consistent way. You could think about doing it in a way that allowed for the groupings to be of different sizes, because maybe there's one cluster is more tightly correlated than others. You could think about many things. This is a simple one, very simple one to implement. Yes? Presumably it depends a lot on what your observables are. Yes. So let me come back to this in just a second. So this is a strategy, right? And it is a coarse graining strategy. I start with n variables. I end up with n over 2 variables. And I can iterate it so that I get to n over 4 variables and so on. And along the way, of course, what I'm doing is grouping together neurons 2 at a time, then 4 at a time, then 8 at a time, and so on. And so I have clusters of strongly correlated groups of neurons. And the coarse-grained variables that are left over is something like the average activity of those neurons. Okay? Remember, since you don't otherwise have a guide to which neurons are connected to which and so on. So that's a proposal for what neighbor means.
Can you comment on the choice of covariance rather than Hess's correlation coefficient?
Yes, you could argue that what you should use is actually, you know what? It probably makes more sense to use the correlation coefficient rather than the... because the system might be sufficiently inhomogeneous that the differences in variance are large. And so I just have a big covariance because I happen to have two things that have a large variance. So we should probably think about using the correlation coefficient. And in fact, that's what we did. So not only is it a good idea, it's actually what we did. Let me make another observation that reaches back to here. So remember I said that part of the point of all this was that you end up deriving things about the behavior on macroscopic scales which are universal. It's clear that in this coarse graining step, there's a certain amount of arbitrariness of exactly how you do it. So none of the universal things can depend on that arbitrariness. On the other hand, the efficiency with which you will find those universal things does depend on the arbitrariness. So in some sense, the choice of exactly what you do in this coarse graining step is both sort of incredibly important and incredibly unimportant, right? So it's unimportant in the sense that nothing that really matters can depend on it, but how efficiently you will find it, either with pen and paper or with analyzing simulations or real data, depends a lot on exactly what you do. So that's a kind of murky area, right? And here we're forced to plunge immediately into that murky area because we don't have there isn't an obvious way of doing it that's given to you a priori, right? Okay. There's a more, so sort of combining the two questions here about what your observables are and exactly what I should use here. You could think about constructing other objects that capture something about the correlations among variables living in different places, right? For example, you could pick higher order correlations. It's not clear, if the thing that lives at each site is already many variables, then there are different combinations of them that you might care about and so on. And so even in this sketch, there are more choices to be made, right? Yes?
So just to be clear, like when you're talking about correlation, what are you really trying to capture? Are you is this kind of a proxy for connectivity? And if so, then why don't we have, is it because we do not have a connectivity map?
So what it's a proxy for is the thing which is real space in the usual case, right? Because remember that when you do things in real space, you coarse grain on scale L. You don't care whether the microscopic interactions are nearest neighbor, second nearest neighbor, 2 spins at a time, 4 spins at a time, right? You don't have to ask that question before you. So in fact, importantly, right, you can do the RG of models that don't have pairwise interactions. So it's not the case that we're looking for a surrogate for connectivity. We're really looking for a surrogate for length scale. And so what we're saying is that a candidate as the substitute for length scale. So remember, what's happening when you do the normalization group is you're averaging over details. And you're going to move the boundary between the details that you average over and the macroscopic things that you take seriously. And conveniently, we make that boundary be a length scale. So the question is, what do we want to put in place of that? We still have the notion that in a system with a large number of degrees of freedom, there are details that I want to average over and macroscopic effects that I want to keep track of. But I know that that boundary isn't at a particular place, so I want to ask what happens as I move it. But how do I even define that boundary? And so one idea is use correlation directly as the definition of that boundary. Okay? Let me also emphasize to you that if you start thinking about the covariance or correlation matrix, then you also have a natural notion of what momentum is. Because with translation invariance, then Cij is really a function of the distance or the vector that connects I to j, right? That's what it means to be translation invariant. It doesn't matter what the absolute position xi and xj are. It only matters what the distance between them is. And if you want to diagonalize, if you think about trying to diagonalize the covariance matrix, then you know that the eigenvectors of the covariance matrix are the momentum states, right? They're the Fourier components. So furthermore, if you then diagonalize, right, then the lambda mu's are just the Fourier transform of the correlation function. And typically, which is usually called, let's call it g of k or something. And usually, that's a monotonically decreasing function of k. So the high momentum components, the short wavelength fluctuations, are the ones that make small contributions, that they correspond to small eigenvalues of the covariance matrix, which means that if you think about the total amount of variance in the system, these components make a small contribution, these components make a large contribution. And so what you're doing when you put a cutoff in momentum space is you're averaging over the components of the fluctuations in the system that make small contributions to the variance. So you might recognize these words. This is what principal components analysis is. Right? When you do principal components analysis, you compute the covariance of the fluctuations of the high dimensional object that you're measuring. You go to the eigenbasis and you say there are directions in space that make small contributions to the variance. There are directions in space that make large contributions to the variance. If you did this for, the two-dimensional Ising model, what you would find is that putting the components in order is putting the momentum components in order. And averaging over the components that make small contributions to the variance is averaging over the short wavelength fluctuations. The important difference to PCA is that often with PCA, the question is, where should you put the cutoff and what are the components that are left over? The lesson of the renormalization group was, first of all, in a translation invariant system, the question is, what are the components is answerable a priori. They're the Fourier components, and so you don't need to do anything else. So obviously it is not the case that the only interesting question is, what are these eigenvectors? Okay. And furthermore, in most systems where you have n interacting degrees of freedom, this spectrum is continuous. So you have no real reason to put the cutoff in any particular place. And so the lesson of the renormalization group is you should ask, as I put the cutoff in one place and look at the joint probability distributions of the variables that are left over, what happens as I move the cutoff? Does the probability distribution get simpler? Does it get more complicated? Does it approach something that I can understand? Okay? So the proposal is that what corresponds to neighborhood is your most correlated partner, and what corresponds to momentum are the principal components. Okay? That's the idea. So now, suppose you implement this. How do you follow the flow of all these coupling constants? Yes?
Sorry, just to make things clear regarding the neighborhood. Just say you find neighbors by maximum correlation.
Yes.
Shouldn't that be the absolute value of the correlation? And it can be very strongly negatively correlated.
Yes. So if you, so in particular, right, if you did this for an antiferromagnet,
Right.
you'd screw up, right? So maybe you should even be a little more sophisticated if the variables actually have complicated probability distributions. So they're neither almost Gaussian nor are they binary. Maybe you should really use the mutual information. And yes, sure. I told you there are lots of options here,
Yeah.
right? It's also true that this whole discussion is about a single snapshot in time. Okay, so I'll let you think about the rest of that sentence, or the rest of that paragraph, actually. So how do you follow the flow? So this is a problem. Obviously, if we were doing these calculations in the context of a model, then you follow the flow by going through the procedure like we did for the decimation of the one-dimensionalizing model. But if I give you data, what do you do? Well, of course, although I think we're the first people to try doing this with data on biological systems, this problem was faced very early on by people who looked at Monte Carlo simulations. So imagine that I show you Monte Carlo simulations of some model. Let's take an Ising model as an example. And you go through coarse graining, either in real space or in Fourier space. And you can do that with the data, right? I give you a snapshot of the configurations of the spins. I average together all the spins that are within neighborhood of some size L. Or I Fourier transform and cut off, transform back, whatever you want to do, right? I can construct the coarse grain variables directly, but what am I going to measure to see what's going on? So one idea is you look at the probability distribution of one coarse grain variable on length scale L, right? I can't look at the joint distribution because there's too many variables. So let me follow one of them. So if you think about the Ising model, then what happens to this probability distribution? Well, it starts out as two delta functions at plus and minus 1, right? At the shortest length scale. But then, as you coarse grain, a couple of different things can happen. One is that if you keep coarse graining, eventually you get to a scale where the spins aren't very strongly correlated anymore, and you're just averaging together things that aren't really correlated at all. The central limit theorem takes over, and you end up with a Gaussian. Another possibility, and this is tricky, depends exactly how it works, right? How n goes to infinity and so on. You could imagine that you end up with two Gaussians that are centered at plus and minus 1. That's because, or maybe you really only see one of them in your simulation, which is more likely. So you take a really big system, you're below the critical temperature, it magnetizes, and it never flips over, right? So what you see are small fluctuations around the magnetized state. But again, this thing becomes Gaussian. And of course, there's something very special that happens at the critical point. Which is that you see some non-Gaussian form. Okay? So this is all as you change L. So one idea of following the flow, right? And of course, if this is what's happening, right, that means that the probability distribution of coarse grain variables is becoming Gaussian. And so it's becoming simple. But it's becoming simple for reasons that we all know. It's the central limit theorem finally coming back to haunt us, right? The non-trivial result of the normalization group is that there are other fixed distributions that you can find other than the Gaussian. What else can you do? In the interest of time, let me tell you about only one other thing you can do, which is to think about your coarse grain variables and how they vary in time. And let me take the connected part, right? So subtract off the averages. So what you may find, so in general, you get a completely different correlation function at every L. But if this whole picture of smoothly changing behavior as a function of your cutoff L is correct, and things are becoming simpler as L becomes larger, then you might expect to see dynamic scaling. in which this will become a function only of a single time scale. And that time scale will vary with length as a power because you're in a regime where there's nothing, right? You're not seeing any behavior with a characteristic length anymore. Okay? So these are examples of the kinds of things you can check for. And I have 20 minutes to tell you what happens when you look at real data. So let's see. So so you get the idea, right? We're going to follow these coarse graining procedures. We're going to do it for real neural data. And we're going to see what happens. Is that the right one? Yes. Good. So where are we going to do this? We're going to do this in a little mouse that lives in David Tank's lab. And it's a very special mouse. It's been genetically engineered so that the neurons in its brain produce a protein which is fluorescent, and the fluorescence depends on the calcium concentration in the neuron. And calcium concentrations vary in response to the electrical activity of the neurons. What you'd really like is a protein that got inserted into the membrane that responded directly to the voltage across the membrane, so you'd be directly monitoring electrical activity. You can do that, but at the moment the signal-to-noise ratio for those probes is not quite as good as it should be. Wait a few years. So in the meantime, you genetically engineer the mouse to make these things. You hold the mouse down so that you can look into its brain with a very high resolution microscope. The cells are big, but the spaces between the cells are very small. So if you want to be able to isolate the cells, you need very high resolution. So this is done with scanning 2-photon microscopy. The movies are synthesized, right? What you really have is a beam that's scanning. It's fluorescence microscopy, so if you make a very small spot, you know that all the fluorescence will come from that spot. So then you just collect all the light. And then you synthesize the image because you're scanning. Okay? So the physics of building that microscope is not trivial. The molecular biology of engineering the mouse, also not trivial. In most interesting regions of the central brain, nothing really happens unless the animal is actually behaving. So on the one hand, you want to be able to look into the mouse's brain with micron or submicron resolution microscopy. On the other hand, you'd like him to be able to run around and do stuff. Those are conflicting with each other. There are different possible solutions. The one that David and his colleagues built is this one. You only care about holding down his head because that's what you want to see. So the rest of him can run around. So you let him run on a styrofoam ball. You suspend the styrofoam ball with a column of air. So he's running, right? You then monitor the motion of the ball with a different kind of mouse. You take the signal of the rotation of the ball and you compute how he would have been moving through three-dimensional space if he had taken that pattern of footsteps. You then run that to a computer and project on a screen in front of the mouse what he would have seen if he'd taken that path. So you've built virtual reality for a mouse. So you have to get all of these things to work at the same time, right? You have to get the molecular biology to work, you have to get the physics of the microscope to work, and you have to get the virtual reality to work. It's a fantastic experiment. The state of the art is that you can do this and you look in particular in the hippocampus where there are the neurons that carry information about the position of the animal in space, these famous place cells, and you can see, for example, in the image that you're looking at here, there's roughly 1,000 neurons that you can distinguish, and you can now do 1,500 or more. There are techniques that allow you to go factor of 2, 3 beyond that, still at high time resolution. If you're willing to give up some time resolution, you can get more neurons. These things are all evolving. Yes?
Neurons are fired, so the fluorescence is the reflection of
The fluorescence is a reflection of neural activity. So let's actually look at it. The fluorescence signals that you see, these are the hashy things are the raw fluorescence signals. So first of all, you see what the signal-to-noise ratio is like. All the theorists in the room. The best thing for analyzing data is really good experimental colleagues, right? Right? If you want to get more out of the data, the best thing is that the quality of the data goes up, right? These guys are fantastic. So it's
I think they're not impressed because, Stephanie told us it's spikes, so now everybody's like, sure, spikes,
Yeah.
it looks like spikes.
Yes. Yeah, so actually these things last too long to be individual spikes. These are the calcium transients that result from that. And you're making a sort of indirect measurement, right? You're measuring the fluorescence that is a consequence of the calcium concentration and so on. So importantly, neurons are not active most of the time. And so you can see the periods in which they are active. And you have a choice whether you want to think about the continuous variable or whether you want to think about a discrete variable that just tells you on or off. Okay? Okay, I've given you this story already that we're going to try and coarse grain these variables. So let's do the coarse graining. We've said, so let's do the real space version. We've said that we're going to use correlations as a surrogate for neighborhood. Let's start with the continuous signal. So here are two neurons that are the most correlated pair that we find. We average those together. Here's the second most correlated. Here's another highly correlated pair. This is the most highly correlated pair at the next stage, so you average those together and so on. There is a slight issue. There's an issue of normalization. Remember that this signal is the fluorescence that is the result of a change in calcium concentration. So the absolute magnitude, it's not clear what it means. And it might mean different things in different neurons because they make different amounts of the protein. So on the other hand, you know what 0 is. That means that nothing's happening. And as you saw in the raw data, 0 is really pretty well defined. So we want to be sure that we maintain what 0 means while getting rid of the arbitrariness of the magnitude. So what we do is we say that the non-zero part of the signal should have an average value of 1. And we should reapply that at every stage of coarse graining, and then you follow the path that I described. So
how do you get the two spikes? 4 seems, why are they correlated? There's nothing.
So this is a little snippet of the data. You'll notice, for example, that 4 and 3 had this event essentially in common. And so that contributes a lot to their correlation. I mean, the correlation is an average over a very long period of time, right? And I'm showing you a short segment. So, I mean, I don't think it's too strong. It takes too much imagination to see that 2, which has events here and here, are strongly correlated with those, and so on, right? Whereas these guys are obviously not very strongly correlated with each other. And if there's any correlation at all, it must come from somewhere else in the data.
It's kind of amazing. Like 2 and 3.
They happen to look more correlated, but actually these events are separated in time. But anyhow, we're still trying to figure out what's the best way of illustrating this. This is actually grabbed from the data, but as I say, correlation is an average over the duration of the experiment. It's possible that a schematic rather than something that really came from the data would be more useful. Okay, I told you how are we going to follow the flow? We're going to look at the probability distribution of the coarse grain variables. Remember, 0 means something, right? So when we've averaged together k neurons, there's still a probability that all k of those neurons were silent, and so as a result, the coarse grain variable is also 0. So you can track that probability, and then the non-zero part of the distribution is normalized so that its mean is equal to 1. So to fix ideas, right, if you were averaging together neurons that were independent of each other, then the probability that they're silent would go down exponentially with the number of neurons that you averaged, right, because it's just the product of probabilities. On the other hand, if they were all perfectly correlated with each other, then the probability wouldn't go down at all, right? So what you actually see is that the probability falls exponentially, but with a non-trivial exponent. And you see that that's true over more than 2 decades, right? So this is the logarithm of this probability as a function of its cluster size k, and you see very nice power law scaling with some non-trivial exponent. If you look at one experiment in one mouse, this is the error bar. If you compare across several different mice, this is the error bar. So what we found is a feature of the collective behavior of this population of neurons. Remember, this was a mouse. There are no identified neurons. So you can go back to the same region of the brain, and statistically things tend to be similar, but there's no sense in which you're revisiting the same neurons in a different sample, right? If you were in a fly, you could revisit the same, or a worm, you could revisit the same neurons. In a mouse, you can just go to the same region of the brain. So we can see, first of all, you see this power law behavior, which is interesting. It tells you that there's some sort of underlying self-similarity. And the reproducibility across animals is extremely high, right? You were worried about something.
No, just, do you have any intuition for the source of this exponent?
I told you, this is phenomenology. I warned you at the beginning. This is the question I was trying to fend off.
Can you repeat, what is the definition of K?
This is the probability that the coarse-grained variable will be 0, right? So if I look at the distribution of the coarse-grained variable, because 0 was a possibility, and for a large part of the time the neuron is silent, and we can denoise the silent part, right?
So what minus average firing rate?
Well, no. It's actually moment by, well, okay, yes. It's the fraction of time that the thing is silent,
Yeah,
okay?
But X is, you look at one neuron or some region or what?
X is the coarse-grained variable after I've grouped together, 2 neurons, 4 neurons, and so on, right? But one at a time.
One at a time.
One at a time, right? I'm not trying to look at joint distributions. I'm looking at one of the coarse-grained variables.
That's magnetization.
Right, so it's the analog of measuring the local magnetization after you've coarse-grained on a scale log K, right? Then if you look at the continuous part of the distribution, what you see is that as you keep coarse-graining, the distribution hardly changes at all, and to the extent that it's changing, it's converging on something that looks almost like just an exponential, right? This variable is positive. So what you're seeing is that as you coarse-grain, the distribution of the coarse-grained variable is approaching a fixed form, and it's not Gaussian. So this is not just the central limit theorem. This is a result of the correlations in the system allowing for some non-trivial distribution to persist scale after scale after scale. Somehow in, transforming from one thing to another, bad things happen, but they can be fixed.
So this is,
So let me, I didn't talk about this one, so let me leave it alone for the moment. Let me focus your attention over here.
I was going to ask for previous thing.
Oh, the previous one, okay.
The mouse doing what? You don't.
Yeah?
This is like assuming that the mouse is still doing the same thing.
Well, the programming of the virtual reality is the same in both cases. But of course,
Statistically the same.
well, the rule for the virtual reality is the same, right? But what the mouse actually did on the particular thing is, of course, different in detail.
But one can imagine, like, let's say you start putting obstacles in his way or something, then maybe this distribution will change.
Right, so there's a whole set of questions about how this all changes when you change the environment in which the animal is moving, and that's a great question. This is an interesting region of the brain because you're sort of it's not a low-level sensory region where you're just directly responding to what you're seeing or feeling, and it's not the motor output, right? It's in that sort of deep space in between where maybe you have a map of what you're planning on doing or where you are and things like that. So let me tell you about the case of the dynamic scaling. So you do the test which I just described over there. You compute the correlation functions after different amounts of coarse graining. You see that they get slower and slower. If you rescale by the correlation time, you see that they collapse, which by itself isn't trivial. And then if you ask how much rescaling did you need as a function of how many neurons have been averaged together to produce the coarse-grained variable, you see a power law. Okay, some.
But so I mean, if you compare the mathematician,
Yes?
0 and 1 is like minus 1 and 1. I mean, the fact that you didn't get a Gaussian, the fact that you got only positive is just because you were
the fact that you only get positive is trivial, is by construction. But the fact that the distribution has a fixed form is not trivial, right? For example, if you took two independent variables out of that distribution and averaged them together, they would start to, and iterated, you would approach a Gaussian whose mean was 1 and whose variance was shrinking.
So what you've done is you've sort of mixed real space with momentum space, right?
Not yet. I mean, if you pay attention to the thing on the left, which I told you not to look at, then you may be. But
With the initial coarse graining you did?
no, the initial coarse graining this was the real space coarse graining, where you just use your most correlated partner. But you can do it all again in momentum space. So I told you how you would do it, right? You diagonalize the covariance matrix. You project onto the components that have the large, that make large contributions to the variance, that have large eigenvalues. And then you ask, how does the probability distribution evolve? And the answer is that it evolves toward a fixed form. So I start with, I've put my cutoff so that I have only, remember I started with more than 1,000 neurons, so I can get rid of 90% of the modes. And that gives me the cyan curve. And I keep going, and you notice that it hardly changes at all. And in the bulk, it really isn't changing. And it's not Gaussian. Right? So you're thinning out. So importantly, right, you're doing PCA. You're averaging over the components that make small contributions to the variance. You keep averaging over more and more of them. And the probability distribution of the variables that are left over has some fixed form, but it's not Gaussian. Okay? And you can redo the dynamic scaling argument. As many of you know now, what you want to do is actually look at the correlation times of the individual modes. And you see that those are a power of the eigenvalue. And in fact, if you put this power together with the things that are, this power should be a combination of the powers that were on the previous graph, and that works, even though they're independent calculations. Yes? I told you there's no theory. Yes?
I mean, I guess you haven't done the theory, but like I was wondering if you like compare this with like a null model. For example, you just have a series of like random spikes. Maybe you fix the mean number of spikes to be
very good. Okay, so let me
no notion of like no
absolutely
no
fine.
neurons,
So
and like how does it compare like exponential?
okay, null model number 1. This is the hippocampus. Neurons respond to place. So let me compute the probability that each neuron is active as a function of position in the virtual environment. And then let me use the actual path that the animal took through the virtual environment and generate samples, assuming that the neurons are independent but of each other, but dependent on position. You do not see scaling. Next null model. Let's randomly connect neurons together in one of the standard ways, generate some activity whose average sort of global statistical properties are similar to this. You see something that might be scaling, but it's going toward the Gaussian fixed point. Okay? There are models that purport to produce behaviors that could be misdiagnosed as being critical. So we studied those models, and they don't do this either. I don't know exactly in what sense they were critical, but I mean, we could talk about that, but they don't do this either. So we have a whole variety of things which are plausible sort of generic network models that capture different parts of these data, and they don't do this. Okay, so I've got 2 minutes. So let me tell you what we think we've learned. So I spent a long time, so the hypothesis for this talk was that if you think about it the right way, what we did is simple. And I don't know whether that's correct. By now, of course, I think that. So that's the way I presented it. The idea is that coarse graining is a path to simplification. So we should try coarse graining high dimensional data explicitly and see what happens. And a priori, you have no idea what's going to happen. I think the default assumption is that if you coarse grain, eventually you're averaging together things that aren't correlated, everything becomes Gaussian, it's not interesting. Not what we see. Okay? You see, and remember that when you coarse grain and you get Gaussians, then the approach to the central limit theorem is itself associated with scaling behaviors, right? The variance is related to the number of things that you average together, either 1 over the number or proportional to the number, depending on whether you averaged or summed, right? So we see the approach to we see the approach to fixed distributions with a non-trivial form, and we see scaling along that path. And so but it's not the Gaussian, right? So in the technical language of the normalization group, it suggests that the behavior of the probability distribution that describes the joint activity of all the neurons in the network is controlled by some non-trivial fixed point. Okay? So this is sort of the best thing you could have hoped to see, right? We had no idea whether we would see it or not, but this is what happened. And so what we spent a lot of time doing is convincing ourselves that this is not an artifact in various ways. There are so a lesson for all the theorists in the audience, every time you analyze data in a new way, you become sensitive to a new set of artifacts that your experimentalist friends hadn't thought about. Okay? It's not that they're bad, it's that they didn't have any reason to think about them until you analyze the data in this way. So what I'm showing you is the result of several passes through the data in which we made discoveries of that flavor, which I will not tell you about. There's all sorts of other reasons why you might get these behaviors for uninteresting reasons. Remember, you're talking about high dimensional data. You have a large but nonetheless limited number of samples. You know that when you look at high dimensional data with a limited number of samples, there's all sorts of very specific artifacts that can arise. You should worry about those. Anyhow, there's lots of things to check. We think that we're seeing real scaling over not quite 3 decades, but let's say more than 2. There's a prospect for seeing more as the experiments get bigger, or not, in which case the story ends. And we're seeing I think more deeply, this approach to a fixed distribution tells you that there's something simple underlying the macroscopic behavior of the system, and now we need to construct a theory for that. So that's 3:30, so let me stop.